Okay, dear students, let us start from where we left last time. Last time I introduced you to what we call the first fundamental form or the metric, which is the expression e du square plus twice f dv plus g dv square, which I denoted by ds square because it is the length of this infinitely small arc ds on the surface R is equal to R at UV. And then EGF are numbers that are evaluated at that point. E is, as I told you last time, R2 dot R2 RU. Okay, F is just RU dot RB, and G is RB dot RB. So this was our first fundamental form. Now we also showed that this expression EG minus F square is equal to h square, which is equal to norm of Ru cross Rv the whole square, which is always going to be positive for a regular point. So this information we have about this first fundamental form. E, F, G are numbers that are called first order fundamental coefficients. So E, F, and G are numbers, or we call them first order fundamental magnitudes or coefficients. We also call them first order fundamental coefficients. Okay, so this is what we did last time. Now we show that this quadratic form, I also told you can write this quadratic form in a simple form as du dv. This is a matrix. Then e f f g multiplied by this column vector du dv. If you multiply this, you should get the expression, the matrix multiplication. So corresponding to every quadratic form, you would find a matrix, a square matrix, which would have certain properties. As is the case, the determinant of this matrix, which would be Eg minus f square, is positive. Another thing about quadratic forms is that, let me add a page. Okay, page 2. Okay, where is the page? Can't change. Okay, next thing we are going to show that this is a positive definite metric. Metric means the first order first fundamental form. Metric is a positive definite positive definite quadratic form, which means that if it's a quadratic form, हमारा जो variable है इस quadratic form में, अगर मैं तुम्हें दिखा दूँ this e du square plus twice f du, what changes? E, F, G are numbers. So what is changing is du and dv. So du and dv is a small change in the parameters u and v. Now when I say this is a quadratic form, this is a quadratic form in these variables du and dv. Now we say that it's a positive, we call a quadratic form a positive definite quadratic form if this is always positive whenever du dv is not equal to 0 0. It can only be 0 when both du and dv are 0. Then obviously it would be 0. Other situation it won't be 0. I mean to say, if du dv both are not equal to 0, then this would not be 0. That's what we mean by a positive definite quadratic form. Now we can prove that. Firstly, we notice that E must be strictly positive, because E is equal to Ru dotted with Ru, which is basically norm of Ru square. Now norm of anything is non-negative, so if I want to show that this is positive, I have to show that this cannot be 0, but this cannot be 0 because if it is equal to 0 would imply that R sub u is equal to 0, which would imply that Ru cross Rv is a null vector. So since we are assuming that our point is regular, this cannot be 0, means this cannot be 0, means this cannot be 0. Now, but this also cannot be negative because it's length. So I can divide by this number because this is a positive number. So that means I can write E, my fundamental form, E du square plus twice f du dv plus g dv square equal to 1 by e. I multiply and divide by e, so it would be e square du square plus twice fe du dv plus ge dv square. But that can be written as 1 by e square du square. I make it a complete square. For that I write twice f e du dv. Then I add, what should I add? I should add f square dv square. Then I also have plus g e dv square. So it is a square plus b square plus 2ab. Then I should have minus f square dv square. So that can be written as, I can write it as 1 by e. I complete the square, so it would be e du plus f dv whole squared. Then plus, I can write it as, if I combine that, eg minus f square times dv square. Eg minus f square whole multiplied by dv square. And if I add a page, so this would be further equal to 1 by e du square, e du plus f dv whole square plus h square dv square. You know that we already know that h square is equal to eg minus f square, and that's also non-negative. Now this is always greater than equal to 0 because it is sum of squares, isn't it? Sum of two positive squares, sum of two squares is always non-negative. Now for all real values of du and dv, for all possible values of du and dv. But if now we want to show that this cannot be 0 if both du and dv are not equal to 0. So for that, now we have if. Now if it is 0, if e du square plus twice f du dv is plus g dv square is equal to 0, and if I go to the previous page, so it means that this thing is 0. I mean to say, it means what I have evaluated here should be equal to 0. So it would imply that e du plus f dv is equal to 0 and h square dv is equal to 0, because sum of squares is 0 if and only if both the numbers are 0. Each of the squares is 0. So because sum here, sum of two squares is 0, so I must have this is equal to 0. Now both, I insist that both must be 0, and So which would imply that since h cannot be 0, h cannot be 0 means dv must be 0 and E du plus f dv must be equal to 0. Now dv 0 means that dv must be equal to 0 and E du must be equal to 0, which means that of course both dv and du must be equal to 0. So if this expression is 0, firstly it is non-negative, secondly it would be 0 if and only if du and dv are equal to 0. So otherwise it would be positive. So that makes it a positive definite quadratic form. So I add another page. So far what we have shown that this is a positive definite quadratic form. Then is the invariance property of the metric. Now invariance property means under a proper parametric transformation, by that I mean to say proper parametric transformation or allowable parametric transformation is one in which regular point goes to the regular point and the singular point goes to the singular point. For that we know that Jacobian of the transformation should not be equal to 0, the Jacobian determinant. So under that proper reparametrization of the surface, the metric remains invariant. The metric does not change. The way we measure the infinite small length does not vary if we reparameterize the surface. So the metric is invariant. The metric is invariant if if u and v are changed to some other parameters, let me call them u prime and v prime, under reparameterization. That's again very easy to prove. So let our reparameterizations be of the type u prime, as I did last time, is equal to phi of uv and v prime is equal to psi of uv. So these are my relations that reparameterize my surface. So then, as we did last time, I don't want to repeat it, Ru prime is equal to R sub u into del u by del prime plus R sub v into del v by del prime. Del v by del u prime and R sub v prime similarly is equal to R sub u del u by del v prime plus R sub v into del v by del v prime. This is just the chain rule. So this is just the chain rule. Similarly, by chain rule or by the definition of the differential, so by the definition of the differential, du can be written as del u by del u prime du plus del u by del v prime dv prime. Now let me write it. Similarly, dv is equal to del v by del u prime du prime plus del v by del v prime into dv prime. So this is just the definition of the differential, what we have done in our first semester, so it's nothing new. So I want to show that, so No, so matlab it is just the reason what I'm trying to say is, since u prime is a function of uv, and this is invertible, no, if it is a reparameterization, this has to be differentiable both ways. By that I mean partial derivatives must exist and must be continuous, and it must be invertible. It must be a bijection within the domain. Whatever patch of the surface we are considering, it must be a bijection there. Therefore, u must also be a function of u and v, some function of, let me call it f u v, and v must be also a function of, in reverse, v must be also a function of some function of, let me call it g u prime v prime. In that case, I can find the differential of u with respect to the changes in u prime and v prime. So this is what I get from there. Now I just have to use it. Now if I denote my new fundamental, first order fundamental magnitudes by E prime, F prime and G prime, these are my first order fundamental magnitudes after the change of parameters. Then if I evaluate E prime du prime square, I mean the plus twice F prime du prime dv prime plus g prime dv prime square, this would be my new metric. Now this can be written as ru prime dot ru prime multiplied by du prime square plus twice ru prime dotted with rv prime du prime dv prime plus r sub v prime dot r sub v prime into dv prime square. Now this is just the definition of the metric. Now this can be written as r sub u prime du prime plus r sub v prime dv prime in norm ka whole square. If you dot this vector with itself, you get exactly the expression above. So this can be further written as, now if I use my equations, so I can write it as, now substituting the value of du prime, okay, so this is what I have now. So I substitute the value for ru prime. Now ru prime, I know by chain rule, is actually r sub u du by du prime plus r sub v into dv by du prime. This is what I have already written. Rv prime is the ru into du by du prime. Sorry, मैं गलत लिख रहा हूँ. This has to be. Let me rewrite it. I have already written the equations for r sub u and r sub v. So in the previous page, I can show you the previous page. Okay. So my equations for r sub u and r sub v are these. R sub u prime is equal to this thing and r sub v prime is equal to this thing. Now I substitute them here. I substitute those values for r sub u prime and r sub v prime. So when I substitute these values, I will put a norm outside it. I will get r sub u del u by del prime plus r sub v into del v by del u prime multiplied by du prime plus r sub u del u by del v prime plus r sub v into del v by del v prime whole multiplied by dv prime in norm ka square. This is what I have. Now I can just rearrange these, which I believe you can do yourself. I can write it as I take Ru common from here and from here. So what do I get? If I take Ru common, I will get del u by del u prime into du prime plus del u by del v prime into del v prime plus r sub v. Similarly, I take these two terms and take rv outside. So I will get del v by del u prime du prime plus del v by del v prime into dv prime whole square. Now I use my earlier equations, these two equations, that du is equal to this thing. I use these two equations and substitute these values exactly. Now if I look at here, I have got exactly the same expressions as in that equation. So this is nothing but Ru. This is nothing but Ru du plus Rv. Now this whole thing is equal to dv. If you look at the previous equation, norm square. And if I expand it via the dot product, so I will get nothing but Ru dot Ru du square plus twice Ru dot Rv du dv plus Rv dot Rv dv square, which is nothing but E du square plus twice f du dv plus g dv square, which is my old fundamental formula when I had parameters as u and v. So under the change of parameters, the metric does not change. Whether I take my metric with respect to old parameters or new parameters, they are same, their values are same. So that was the invariance property of the metric. Then before going any further, I will talk about what we call the intrinsic properties of a surface. Now intrinsic property of a surface is one which does not depend on the equation of the surface. Does not depend upon the equation of the surface. By that, does not depend upon the, what's our equation of the surface? R is equal to RFUV, and this is basically the coordinates. You have got x coordinate, which depends upon UV, y coordinates, and then z coordinate. So equation of the surface tells us about its, I've got a surface inside 3 dimensions, and once I recognize that it lies inside 3 dimensions, so it has got an x coordinate, a y coordinate, and z coordinate, which is given by the equation of the surface. So the intrinsic property of a surface is one which does not depend, which does not depend how it lies inside the ambient space of 3 dimensions. It has got no reference to our ambient space, no reference to the equation. And if a property of a surface depends upon the equation of the surface, then it's called non-intrinsic. Now, one of the main theorems that we are going to do is that the Gaussian curvature theorem egregium, it's called, that Gaussian curvature or curvature of a surface, which we have yet to define, is intrinsic. It does not depend upon the equation of this surface. It does not depend upon how the surface is inside, how it lies inside the ambient three-dimensional space. So let me come to our next topic, that is our second fundamental form. Now, second fundamental form, let me take another page. So let us define what is called second fundamental form of the surface. Second, now first fundamental form is about infinitesimal length, the length of a small arc on a certain surface. Now, second fundamental form is basically how much the surface is bent at a certain point. You can say it has got something to do with the curvature of a surface at a certain point. So let us first define it. So let our surface be as usual r vector, which depends upon two parameters, and then we define the second fundamental form. It's again a fundamental form in du and dv. So it's a quadratic, what we call differential form. By differential, I mean its variables are differentials. Now, what varies is a small change in u and small change in v. That means it's of the form L. We write it as L du square plus twice m du dv plus g dv square. So it's called second fundamental form, where the quantities, ये जो L, M, N है, these are again numbers that are evaluated at a point on a surface. These are called second order fundamental magnitudes or quantities, second order fundamental coefficients, quantities, magnitudes. Basically, they are numbers that we evaluate. We evaluate it like this. So we first denote our notation r sub uu. Now, by r sub uu we mean del square r by del u square. And similarly, we denote by r sub uv the quantity del square respective r del u del v, and since we are assuming it to be of class second, it should be the same thing as del square r del v del u. If the first order partial derivatives are continuous, then the mixed partial derivatives are equal, and I can also then denote it as rvu. And similarly, the third second order partial derivative, rather the fourth, would be del square r by del v square. So once we are done with the notations, and then we also have what we call unit normal to the surface. We have already met it before. It is nothing but the normal to the tangent plane at a point, the unit normal, because we are dividing it by its magnitude. So once these are settled, we define, with the help of these quantities, we define our L, M, and N. And L is defined to be now, it is basically the projection of this R UU and R UV and R VV along the norm, along n, along unit norm. By that I mean L is equal to n unit normal dot r sub u, m is equal to again this n vector dot r sub uv, and n is equal to this number n is the magnitude, is the dot product of n dot rvv, and we usually denote ln minus m square is equal to t square. It means nothing, we just denote it by a number t. It has got nothing to do with, just like we had eg minus f square is equal to h square, but there h square had a meaning. Here t is just a notation, a shorthand for ln minus m square, because we are going to use it. So under these definitions, I have now got a quadratic form in du dv of the form L du square plus twice m du dv plus n dv square. This is our second fundamental form. Now the question is, what is second fundamental? What does it entail? What does it mean? First fundamental form had a meaning as the square of an infinitesimal distance on the arc. So what does this expression mean? That's what we are going to do next. The geometrical interpretation. What does it mean geometrically on a surface? The geometrical interpretation of the second fundamental form. For that, we take a surface. Now let me invert it to just make it a little. Let me hope I can first draw it properly. Okay. So if I draw it properly, let me try. Flexible. I'm just inverting it just to make it look a little easier. Okay. So let me try again. Okay, this is just this. Imagine it's just a surface, right? And I take a point here, P. P is a point. Then I take another neighboring point Q. It is the neighboring point, which I denote by Q. Okay. And then I take the tangent plane at P. Let me see if I can draw it properly. So it's a plane which just touches at this point. Okay, so a tangent plane at P, and then I draw a perpendicular from this neighboring point to. So remember that I would have a normal here. At point P, I have got this unit vector n, which is perpendicular to the tangent plane. I draw a perpendicular from this neighboring point Q to the tangent plane at P. Let it intersect the tangent plane at the point R. So this is QR. Now remember that if this surface was flat at this point, then this QR must be equal to 0. And furthermore, since n is perpendicular to the tangent plane at P, QR is also perpendicular to the tangent plane, then this vector n and this QR, let me call it vector or whatever, they are parallel to each other. So they are parallel to each other. Now actually this second fundamental form gives us a measure of this QR, and remember that if it is 0, then the surface must be flat there. If it is large, then the surface must be very curved at the point P, and if it is a small number, then the surface must be less curved at this point. Now we will show that this length, how is it related, how is this length QR related to the second fundamental form. Now for that, what we do, we say let P be denoted by a point on, let it let its position be given by the vector r at uv, and let the point q be given by, since it is a neighboring point, at the point u plus du. We just give a small increment to our variables to get to the neighboring point q. And once we have done that, let dr be the difference of these two vectors. By that I mean, let dr be the r at u plus du, v plus dv minus r at uv. It means this is basically this vector pq. This is basically the vector pq. Vector pq. So it is the difference of two vectors, just the triangle law of vectors, nothing more than that. So once I have done that, now what I do, I write it as r at uv plus this dr is equal to r at u plus du v plus dv. Now since our surface is supposed to be smooth, its partial derivatives exist, I apply Taylor's series. Now since this is a function of two variables, of the function of two variables that we have done in our first semester, I apply that to my function r, which is a function of two variables. So once I do that, I can expand it as it would be equal to first r at uv plus r sub u du plus r sub v dv, then plus 1 by 2 factorial into r sub uu du square plus twice r. You can check it with what we had done, the second order, the Taylor series for the function of two variables. You can check it from your first semester notes, and you will see that this is what we get there, plus r sub dv dv square plus so on and so forth, the higher order partial derivatives. So this is going to be our expression, and as we can see, we can just cancel this ruv and ruv, so that we get pq vector, which is the vector dr is equal to what? What was that? Okay, let us look at the previous pages. It is equal to it is ru du. Okay, it is equal to r sub u du plus r sub v dv plus 1 by 2 into ruu du square plus r sub uv du dv twice plus r sub vv dv square plus so on and so forth, higher order terms. Now what I do, I look at, now remember my surface. Let me again draw it here. Oh, the problem with this ball is that okay. So I wish I could refer to the previous page quickly. Now this is my PQ. Now what I do, I had a situation like this. If this was my surface, I have a point here, then I have another point on the surface. This is my point P. This is my point Q. and then I have what we call a tangent plane at the point P. Or let this point be here just to make it a little easier. It is touching this. So this vector here, PQ, this vector is my dr, and I just drew a perpendicular to this tangent plane. Then I also have the unit normal vector which is perpendicular to the tangent plane. Then if I look at it, this QR is nothing but the projection of PQ on the normal, on the unit normal. So if I take the projection, I put a light here, put this projection of this vector, it would be exactly equal to QR. So that is the same thing. Once I project a vector on a unit vector, it is nothing but the dot product. Projection of a vector on a unit vector would be dot product with that vector. It is the definition of the dot product. So if I now find the dot product of PQ with n, I take the dot product of this vector, this whole expression, into multiplied dotted with n. What do I get? Now remember that n is the cross product of scaled version of Ru cross Rv. So it means that n is perpendicular to both Ru and Rv. So when I take the dot product, what I would get is that the dot product of n with this part would be 0 because n is perpendicular to both Ru and Rv. So therefore dot product would be 0 with n. So what I would have would be the remaining terms, dot product of n with the remaining terms. And if I let du dv become very small, I am assuming that this q is very close to p. So the higher order terms would become insignificant, they would approach 0 before lower order terms. So the only thing possibly I would have, as du dv become very small, I would have 1 by 2 into ruu dot n du square plus twice r sub v dot n du dv plus r sub vv dot n dv square. So this is what I would get by taking this point q very close to p. I am just looking at the neighboring points of p very close, so I can neglect the higher order terms because they would become insignificant as du dv become very small. So which is nothing but my second order fundamental form. It is L du square plus twice m du dv plus n dv square. We have already defined that. So QR, but what does this QR measure? QR is nothing but how curved the surface is at P. Now if we have a bigger value, then the curvature must be higher at this point P, because at the neighboring point, this length, when I draw this perpendicular from Q to the tangent plane at P, would be bigger in case the curvature is more, and it would be 0 if it is flat. So that is the geometrical interpretation of the second fundamental form. So if I leave it here, no, before leaving we can just, okay, let's stop it here. I will see you in the next lecture.